afternoon to everybody. My name is Ljiljana Dekić, and I work in Republic Hydro-meteorological Service of Serbia as head of operational numerical weather prediction department. I will tell you more about WRF NMM modeling system, but for the students who don't have meteorological background, I will tell a few basic, just brief introduction to numerical weather prediction. What is actually numerical weather prediction? You already saw so many plots with the outputs from the model, but basically numerical weather prediction is a science of obtaining the future state of the atmosphere using numerical models, which means that if we assume that if you know initial state, if we have an observation, and if you know equations, and if we can solve that equations, we can have a future state of the atmosphere, or in other words, to make a forecast. Well, most of that equations are nonlinear differential equations, so numerical models are actually computer programs that can solve all that set of physical equations using different numerical solutions, approximations, parameterizations, and all different other things developed during last decades. Also, the basic concept of NWP, numerical weather prediction, is to divide atmosphere into grid boxes. And if we solve, the idea is if we solve equation in one point of that grid box, that will represent the parameters in the whole volume of a grid box. That is how we are solving dynamic. But when we are talking about physical processes in a model, there are a lot of things that we have to include. Physical processes like radiation, transpiration, rainfall, planetary boundary layer, microphysics, etc., etc. And if we are able to include more of that processes, we will have a better focus. This is one nice picture from ECMWF office, probably you know from Exeter, showing how model domains can be from global to regional, from horizontal resolution from about 100 kilometers to 1 kilometer, and sometimes less. But for running regional model, we have to provide initial and lateral boundary conditions from global model. Or abbreviation is usually IC and LBC. And after that, we have to put all these fields through preprocessing. And I was listening to some of your questions about where and how to use grid data from global model. Actually, we were using ECMWF fields, but only for initial and boundary conditions for our model. Specifically for WRF NMM, I can talk later. So if we decide to use limited area model, what we always need and require is initial and boundary conditions, which means meteorological fields on the boundaries, and they are output from global model. Antonio Parodi asked me to mention those two sources of possible initial and lateral boundary conditions. One is from European Center for Medium Range Weather Focus, from the Integrated Focus System IFS, and the link is here. And also from National Centers for Environmental Prediction, or ANSEP, and they call the Global Focus System GFS. I'm not sure if I can use that link from here through the presentation, but you can go to that link And of course, it will take you to Mars. It is Meteorological Archive and Retrieval System of ECMWF. And then you can try to find all the data. Of course, you have to be registered before that. And similar things for GFS, but I'm not sure that you have to have your ID for GFS. In one word, you can find boundary conditions if you want to run your own model. And a few words about preprocessing. It is a set of programs for preparing static data like orography, vegetation, soil types, albedos, sea surface temperature, etc., etc. And after that, we are doing interpolation from coarse grid from global model data to final resolution of our regional limited area model. And after that, we have to do to merge all of those two processes and to horizontally interpolate meteorological fields from ungrid to domain grid, which is defined by geogrid in WRF. Practically, I'm trying to say a few steps ahead, but because if we are using WRF, we have geogrid and then ungrid, and after that, medgrid. You can do that using DRIHM portal, and you will see later how it is working. What maybe can be important about talking about these processes in limited area modeling, and especially if you are talking about flash floods, they're usually caused by convective precipitation. All global models use hydrostatic equation, which assumes an exact equilibrium between the vertical component of pressure gradient force and gravitational force, which means there is no vertical velocity. But when vertical accelerations are small and compared to gravitational acceleration, that hydrostatic approximation is valid. If we are talking about convective processes with very big vertical velocity, that can't be neglected. And most of mesoscale processes and things that we are using in DRIHM are very highly non-hydrostatic. And all present regional and mesoscale model are non-hydrostatic with the horizontal resolution an order of 1 kilometer. And now, what is really WRF NMM, and WRF ARW? Some of the presenters already mentioned them. WRF is actually an acronym of Weather Research and Forecasting. That's a system developed in NCAR and ANSEP in USA. And WRF has two dynamical cores, NMM, which means non-hydrostatic mesoscale model, and Advanced and Research WRF, or ARW. I will tell you more about WRF NMM, which is portable, flexible, state-of-the-art numerical weather prediction model, and very suitable for real-time and WB for operational forecast and research. And here is the link where you can download the model and all the components of the model pre-processing. For pre-processing, also some technical notes, documentations, and if you want to download code or some input data, you have to register first. And I can tell you that I think it was 2006 when I started with this, and then 2007 in August, WRF NMM started to be operational model in our service. So actually, I can say that everybody can do that. What you need is computer, nothing more. And this is how it looks, WRF NMM flowchart. First, you have to provide terrestrial data, but also there are links that you can download, all of them. It's usually called geodata. Then you need to provide model data from global data for running preprocessing to WPS through 3 phases that I already mentioned, GeoGrid, NumGrid, and MetGrid. And the outputs of WPS is NMM, which means meteorological fields for NMM running. And first, you are running real NMM, which is real data initialization. And the outputs of this model is WRF input and WRF boundaries. And after that, WRF NMM core is running, and the outputs of WRF NMM is WRF out DO1 or netcdf files. Well, not exactly netcdf files. That is what we were doing in DRIHM, made so-called bridge to transform those netcdf files in very specific grids to latitude and longitude. So now, during the processing of DRIHMification, we are able to create outputs from WRF NMM and then to transform in netcdf CF convention, which is standardized for every model in DRIHM. And of course, after WRF out, there is some post-processing from specific grid in NMM to latitude, longitude, or some other grid that you're using, and some graphical packages that you can use. So I would like to emphasize that before DRIHM, we could use WRF out, and of course we were using, but using only that netcdf files in grid that WRF NMM is using, and I will tell you more about that grid after. WRF NMM is specific, and they have it's a model with one special approach, like splitting all the equations in hydrostatic and non-hydrostatic contribution. Actually, you can run your WRF NMM like hydro or non-hydro solution. Like you have a question, do I really need non-hydro parts? If I don't need them, if my resolution is more than 10 kilometers, then I will run only hydrostatic part. The original idea of WRF NMM is by Professor Ljiljana. Actually, he is a professor from Belgrade, and I'm very proud that I can say that he was also my professor. And his idea was to split hydrostatic and non-hydrostatic processes, which means that we can be computationally efficient because we are not solving a whole system of equations in every step and in every resolution. Vertical coordinate in WRF NMM is hybrid sigma pressure. Probably you already heard about that. And the grid staggering is semi-staggered Arakawa Egrid. And what is very important is that dynamic of that model is conserve energy and entropy, which can cause a very big noise, numerical noise during the solving of equations. And WRF NMM is also specific because it used a rotated latitude-longitude coordinate system. Idea is very old, starting from the old ETA model from 1970s. And you will see when you will use your DRIHM portal, if you choose your domain, and these dots could be like numerical points when we are actually solving the equations. what we are doing in rotated latitude-longitude coordinate system is to translate this part in a way that equator and prime meridian are the center of the model domain. This process minimizes the convergence of the meridians. So actually you have a rectangular grid that you can easily solve all the equations, and it's more uniform than Earth relative grid, and there is a very small convergence of meridian. This is how this point is coming to this point, and all the calculation is doing here, and then in the process of post-processing we are coming back to the regular grid. And how does it look on the map? The calculation is made here, but after that, when we have to present this in regular latitude-longitude map domain, we have all curved line on the boundaries. And what we wanted to have is nice rectangular map. So it should blink. No. Yeah. This is like information to keep in mind this picture, because if you want to make nice rectangular map from this, you have to remove all of these points on the boundaries of these curved lines. When you choose your domain through the DRIHM portal for WRF NMM, you have to keep in mind that you will lose some few rows on the boundaries of your domain. And what is semi-staggered Arakawa Egrid? It's staggered and rotated for 45 degrees. And again, idea is to keep energy and entropy conserving and momentum advection. And in all those, I'm not sure if you can see, but pluses are different from this point. In this point, you are calculating only, we are calling H points, only mass variables like temperature, like other things which is color. And in plus points, you are calculating only U and V. That means that you don't calculate a whole set of parameters in every point, which is very efficient and more effective than schemes, for example, in Egrid. And the idea is to think diagonally, because resolution of the model is D, is distance between two H points, and this is conventional grid spacing. This is one small table. You will have more in your manuals, how to choose your resolution, because actually this is resolution, not dx or dy, but D is resolution in Egrid. So if you choose grid spacing in preprocessing and WRF name list, that is dx and dy, and specified in fractions of a degree for the WRF NMM, which is not very common. But if you use in DRIHM portal, DRIHM portal will take care about that. So your input grid spacing of D in kilometers, and DRIHM portal will compute the angular distances of dx and dy for the name list that you need for running preprocessing as well as model. And what is about vertical coordinate? That famous Arakawa and Lam hybrid coordinate. It's terrain following pressure coordinate with desirable properties of sigma coordinate. Basically, it's an idea to have a sigma coordinate near the surface, and from some height to have pressure coordinate. And what is desirable properties is exact mass conservation, non-divergent flow remains on the pressure surfaces, there is no problems with weak static stability, and there is no discontinuities. And what is additional benefits from a hybrid, because if you're using sigma coordinate through whole atmosphere, you're still keeping terrain following even if you don't need after some height. It is usually the boundary between sigma and pressure is about 400 hectopascals or 420. But you don't care about that because in the name list you have only values from 1 to 0. And it is applied over the entire atmosphere. This is how it looks. Using sigma range, because you can't neglect all the orography and terrain that you have. But after some height, that there is no impact of the orography, you can use, and you are using, pressure coordinate. And the equation of how to present whole atmospheric pressure, that means hydrostatic and non-hydrostatic pressure, is to use part from sigma and part from pressure range. And dynamics in WRF NMM, as I told already, is dynamic for inviscid adiabatic sigma form, analogous to a hydrostatic system, and then we are introducing two parameters, P and epsilon, and also original idea of Professor Janić. And P is the total or non-hydrostatic pressure, and epsilon is defined as a ratio of vertical acceleration and gravity. And this is a definition, which means that we have independent prognostic equation for W, which means vertical velocity. So we are including vertical velocity through the parameter epsilon. What you can say that if we use 0, it is common hydrostatic approach. For most of the cases, epsilon is much less than 1 in meso and large scale atmospheric flows. But in the situation when we have impact of non-hydrostatic dynamics, especially when we have convection, and when we have resolution less than 10 kilometers, we have to include non-hydrostatic processes, and they are becoming important and very important, and horizontal resolution of about 1 kilometer. And this is like a boundary between using hydrostatic or non-hydrostatic. It says that you can use hydrostatic approximation until about 1 kilometer, because even in large vertical acceleration, that parameter epsilon produces the very low pressure deviations. And dynamical equations are divided in hydrostatic part, 4 of them, momentum equation, thermodynamic equation, hydrostatic continuity, and hypsometric equation, and non-hydrostatic part that we are including or excluding. We have a switch for non-hydrostatic and non-hydrostatic in WRF NMM. Those 3 equations for non-hydrostatic variable definition, third equation of motion, and non-hydrostatic continuity equation. And those are 2 papers for somebody who maybe want to know more about that alternative approach of non-hydrostatic modeling, which is only in WRF NMM. And those are equations, like our project leader Antonio said, for scary students. But it's not really for scary. It's one momentum equation, as I told, thermodynamic equation, hydrostatic continuity, and hypsometric, and those 3 equations that are describing non-hydrostatic processes in WRF NMM. So if we choose to use only hydrostatic part, we are not solving this. Model knows already that that there is no calculation of this part of the model. And then about WRF physics. This is similar in both WRF cores. We have a possibility through name lists to include different physics and different parameterization schemes. And there are also few things that we have to think about. First of all, we have to include radiation, long wave and short wave radiation, then surface in a way that we have to treat surface layer, the lowest layer in the atmosphere, and land water surface, then PBL or planetary boundary layer, then cumulus parameterization, microphysics, what is happening in the clouds, and turbulence and diffusion. And this is a nice plot what we have to include in physics and how it is doing in WRF physics. Those are acronyms or parameters that you have to put or you can change in your name list and use different approach in physics and different parameterization scheme. There is a lot of things that you have to include in radiation, and this is illustration of what is doing what is happening in free atmosphere radiation processes. We have to start from short wave radiation from sun, and if there's a clear sky, there is something that is reflected from surface if there is albedo, and some of that short radiation is absorbed by the surface, and then there is surface emissivity in a long wave, and also there is scattering from clear sky, from clouds, reflection, and more processes you can include. That is, you have more chance to better explain all that happen in radiation. And how it is doing in WRF. You available few radiation schemes, and you can include them through the name list. And available radiation schemes for long wave is radiation, RA, LW, like long wave and short wave physics in both WRF cores, in NMM and advanced and research. And all of them are in name list input. When you see a portal, you can easily recognize what I'm talking about. And for example, if you're using for short wave physics, if you're using 99, that means that we are using GFDL long wave scheme that is used as NMM. But also we have to know that GFDL works only with Fourier microphysics. That means that we have to remove, define, and to recompile that NMM model if we want to use GFDL and not to use Fourier microphysics. And also the closed spectral scheme from global model uses tables, interacts with clouds, ozone profile based on season, latitude, and the carbon dioxide is fixed. There are many documentation about all of this scheme for radiation and other physical process. I'm showing you just an example, and in your manuals you will have all possible options for including, for example, radiation. And also radiation is too expensive if we are talking about computer time to call in every step. So we are trying to adjust a few steps how to resolve cloud cover changes with time. And there are a few parameters for advanced research version is radiation time, like RAD-T. It is 1 minute per kilometer grid size. So think about that. If you choose DX like 10 kilometers, you should choose 10 minutes for radiation. And in NMN, it's different. You have a number of radiation steps for short wave and for long wave, and number of you can calculate that for number of fundamental steps per radiation call is like operational settings should be 3600 by DT, but for high resolution, this one can be used. And what Olivier was telling about comparing models. In some of our tests, we are using 3,600, and we had better result with 1,800, for example. And what about surface physics? There are a few surface physics components. What we have to calculate in every model is atmospheric surface layer, and that model is calculating exchange coefficient for heat and moisture and sending that information to land surface model, and land surface model is calculating land surface fluxes of heat and moisture and calculating soil temperature, soil moisture, snow, if there is a snow melting, snow depth, and sending that information and values to PBL. And also from atmospheric surface layer, we have values for friction stress and water surface fluxes of heat and moisture. And how we can choose? We can also choose from name lists surface layer physics. There is several options for surface layer physics also. What is default is NMM is 2, which means that we are using Monino-Bukov similarity theory with substantial modifications of Professor Janić. And also in this surface physics, you will use Zelitinkiewicz thermal roughness length, very new and very specific parameter in surface physics. And but limitation is that you can use these two only if you use PBL options of 2 and 9, which is Betz-Miller-Janić, for example. And what is happening with surface processes, and this is the part that is we are most interested in DRIHM projects. There are several processes that we have to include in land surface scheme. First, we are starting from precipitation, then have to calculate runoff, some interception, what is happening to the soil moisture fluxes, what is the interflow, transpiration, evapotranspiration, evaporation from open water, if there is a snow melting, interception of water from that snow melting, etc., etc. And in most of the meteorological models, we are using only four soil layers to about 2 meters. Default in NMM also is NOAA land surface model that can be also a standalone model. It is 2 in the name list, and this scheme included vegetation effects, predicts soil temperature, soil moisture in 4 layers, and diagnoses skin temperature. There is prediction of snow cover and canopy moisture, and there is fraction of snow cover and frozen soil. In IRW, you have also like addition of surface urban physics. There is no that part in NMM. And what we are talking in planetary boundary layer, there is a few hundred meters of extreme turbulent motion. What we have from previous slide, if we know and if we calculate a flux, latent heat flux and sensible heat flux, and put this in the model for calculating physics in PBL layers, we have to include local mixing, non-local mixing, and to estimate PBL depth, and to go with entrainment or not if we want to include also vertical diffusion between PBL and free atmosphere. And this is how we can use that in NMM. Quantities are changing rapidly. turbulence and vertical mixing is strong. And of course, there is no equation. We can't use equation to describe all these processes, so we are using parameterization schemes. So there are few parameterization schemes that you can use for calculating boundary layer fluxes like heat, moisture, and momentum. And of course, vertical diffusion. Default in NMM is 2, and of course, Mellor-Yamada-Janich, PBL 1.2 order, that probably doesn't mean anything to you. And there is also turbulent kinetic energy prediction in this scheme. There is advection of turbulent kinetic energy in Mellor-Yamada-Janich is advected only in NMM. There are some slight difference between two cores. And again, you can use a number of physics steps between PBL, calculating PBL and turbulence and length scheme in NMM. And if you use 0 as BLDT and in ARW, that means that you will call this physics in every numerical steps, every time step that you already choose in your name list. And what about cumulus parameterization? It is a calculation of atmospheric heat and moisture and cloud tendencies and surface rainfall. This is like a very simplified scheme what is really happening between boundary layer, between convective clouds with updraft and downdraft. And of course, if you have a hydrostatic model, we can't see anything of this. And cumulus parameterization also had several options in WRF. And in NMM, if we are using 2, it is Betz-Miller-Janich. It is actually Betz-Miller adjustment type scheme for deep and shallow convection, but with involving cloud efficiency as a new parameter that that we can post-convective profile can be unsaturated also in Betz-Miller-Janich scheme. There is no explicit updraft and downdraft and no cloud detrainment. It would be too expensive to put all of that processes, too expensive in computation time. And again, differences between ARW, difference in parameters, time step between cumulus scheme calls is cumulus DT or NCNWS in NMM. And usually this parameter is 10, the same as number of steps between calling physics in the model. And what is happening really in the clouds and microphysics? Microphysics is doing simulation of cloud water, including supercooled cloud water, rain, drizzle, freezing rain, freezing drizzle, snow, snow pellets, ice pellets, and hail, and everything, every kind of particles that can be in the clouds. There's a lot of things and a lot of changes between those particles. There are some illustrations of how we can start from simple, like convective to what can happen in clouds. Like condensate can be rain, and rain can become vapor, and again there is possible transferring from vapor to condensate. And if we involve 0 degree, that means that we can have cloud ice, cloud snow, and again cloud vapor, and changing and transferring between vapor, ice, snow, and of course cloud ice can become cloud condensate, then again rain, then rain can become vapor, and rain can become snow, etc., etc. And there are several of microphysics processes, and then include, I don't even want to talk about this one. So if you include more of that changing and interaction, probably your focus will be much better if we are talking about microphysics and especially convective precipitation. And you can, in microphysics, you can use single and double momentum schemes. Single momentum schemes have one prediction equation only for mass and particle size distribution, and double momentum schemes add a prediction equation for number of concentration. And there is also fall terms in microphysics. And actually, what is not in the cloud has fall terms and terms of particles, and what can go from the except cloud water can have a fall term. But for long time steps, if you are choosing, for example, 60 seconds, drops may fall more than a grid level in a time step. And that means that we have a problem, then we require splitting the time step or some other process. And microphysics can also be chosen in name list. For example, if we use Fourier scheme, also with that GFDL I'm talking on a few slides before. It is designed for efficiency. Advection only total condensate and vapor, but we have diagnostic cloud water, rain, ice, cloud ice, snow, graupel from storage rays, supercooled liquid water and ice melt, variable density for precipitation ice, snow and graupel and sleet, like different ice pellets. And the recommendation is, it is not necessary to use the graupel scheme if you have dx bigger than 10 kilometers. And there is no resolving of graupel in updraft. And cheaper schemes sometimes may give similar results. And when resolving individual updrafts, graupel scheme should be used. And if you are using nesting, and you will hear more about nesting after, all domains should use the same option for microphysics. And as rainfall output, those two cores has different outputs. For ARW, cumulus and microphysics can be run at the same time, and the output is rain C from cumulus scheme and rain NC from microphysics scheme. So we have total precipitation is rain NC, rain C plus rain NC, and rain NCV is in every time step value. And also with snow, which is calculating as a subset of rain. And in NMM it is different. Because NMM outputs rainfall accumulation in millimeter is T-press and controls zeroing out of frequency. It's not accumulated all the focus period. And AC press is the total precipitation. CU press is precipitation comes from cumulus scheme, and the microphysics part is AC press minus Q press. And what we can say about direct interaction of parameterization between cumulus, microphysics, radiation, surface, PBL, all of them is connected, and all of them have had more or less impact to other processes. And in advanced research version, there is only in that part is included turbulence and diffusion, and in name list is like different option. WRF can run with no diffusion, of course. So as a conclusion, you have 7 major physics categories for microphysics, long wave, short wave, surface layer, surface, PBL, and cumulus physics. And all of them and all of those values you can use changing in name list input and then run WRF or WRF NMM. And all of them you can see and change through the DRIHM portal. Otherwise, it's not so easy job. You can open that name list and change and run your model again. Well, that will be all. Thank you. Questions?
I couldn't understand part of your surface or length types. I mean that let's assume that these rooms are grid and the surface can be ice, can be water, can be trees or desert. So all these all affect the albedo or the other coefficients of the model. So how do you solve this problem? Or what are the options for the vegetation types in the model?
Actually, you are asking me how you are involving the soil types and vegetation types.
Yes, what are the options? I don't know.
When I told you about pre-processing, you are doing that part in pre-processing. In pre-processing, you are reading static data, and usually you have a vegetation option like seasonal. And program is doing like what month is now, so vegetation type for that resolution for your grid box is like that. There's categorized in classes, and the same is for soil type, same for ST for sea surface. So you are doing that part and preparing the statistical data in pre-processing before running the model.
What's for the parameterizations in the DRIHM environment? The user can modify the name list or
Yes, user can modify name list. I mean, you can do that if you install WRF NMM or other and you can do it by yourself. But you will see next days how you can use DRIHM portal, and probably Elizabeth will tell you more about that. How can you use DRIHM portal for doing that easily and user friendly?
one question. You just pointed out that all these parameters are implemented simultaneously for all your grids. Is it correct? I mean, in your outer domain and inner domain, all physical parameters will be kept the same.
Yes. First thing, if you are talking about parameters, about physical options that you want to include, first thing is to choose domain. And after you're choosing domain, you will prepare static data, and then running model with options that you already choose. So if you choose a domain, the whole physical options will be running on the whole domain. And if you are using nested model, the same thing. Maybe you can change slightly some things, but there are some recommendations what you would have to do.
The number of parameterization schemes, I mean, your choice could be a little bit different for your outer domain.
Yes.
Okay.
You can choose different options, different physical options
for
in parent and nested domain. Yes.